Hi, everyone. So, yeah, I was just kind of winging it a little bit because I'm trying to bridge the gap between what Shawei's doing and what Brendan's doing. So Brendan's going to show you shortly the way he writes stuff in native Bitcoin script. And, you know, I think if you just jump straight into what he's doing, it might be a little bit overwhelming. So I'm going to sort of show you a few things that are happening here. So when Shawei presented that script context, that's what he's calling that. But we've also got this thing called the sig hash pre-image, which is the same thing. If you're looking at Shawei, he had some of the data values in different spots. Yeah, sorry, I'll put that up. Yeah. Oh. All right, great. So some of his values were in different positions, but all these are essentially the data inputs that are being put into the pre-image, and the pre-image is the data element that will be hashed to create the message that is signed in a Bitcoin transaction. So are you guys familiar with the signing process at all? Do you know anything about the ECDSA algorithm? The input message in this case would be that pre-image data structure. So it was all those different fields or the script context. And then we put it through a hash function to create a fixed 32-byte output. And then we sign that with our private key. So that process is essentially just using that elliptic curve and doing these under the hood steps that you don't really have to worry about, but it will generate a unique numerical value within a 256-bit space. So there's essentially 1.15 times 10 to the 77 values that it could possibly be to. And then when you provide the signed message, so that is the signed Bitcoin transaction, and the node to evaluate whether or not that is a valid signature will have to recreate that input message. So the node will pull some of those values from the transaction data that you've provided, and it will also look into its sort of container, having the record of all the available UTXOs, and check that it will provide the value fields and some of these other elements into it to recreate that pre-image and hash it. So then with this algorithm in this calculations process, it can check that the private key that signed that has a mathematical relationship with the public key that was provided in the transaction data. So in that, you've probably seen that P to PKH transaction type, which is the pay to public key hash. And in that, you will provide your public key and you will provide the signature. And then the node will check that that signature is valid against the message that it recreates as that script context or as that pre-image. So if we think about what that pre-image is asking us, when I get back to this one, yeah. So some of these data fields are required to be, just the raw data themselves, and some of them are the hashings of a data element, so hash prevouts, hash sequence, and hash outputs. So when we're hashing those values, it's going to provide, even if you have 100 inputs that are going into it, so that would be the hash of the previous outs will be the digest of all those inputs chained together. So, if your transaction has 3, you will be providing the TX ID that input that you're spending comes from, and the index position of that output from, within all the outputs that was generated by that transaction. And that might be, a really big value, and then you hash it to create that fixed length value, but it also, by hashing it, it sort of makes them adhere to that same script, and you can't then add inputs after the fact. So these are sort of a security mechanism as well by putting these values in the pre-image. But in some cases, we might not want to sign the inputs of a transaction or all of the inputs because we want to be able to add inputs after the fact we've generated the signatures without affecting the signature itself. So in that case, depending upon that last value 11 down there is the sig hash flag. So the sig hash flag will specify whether we're signing all of the inputs and all of the outputs, or all of the inputs and one of the outputs, which matches the corresponding index position of the input you're signing, or we'll specify if we're going to sign none of the outputs whatsoever. So that would be sig hash all, sig hash single, or sig hash none. And then we can add another modifier to that sig hash flag, and that will specify which of the inputs are also being signed. So then it prefaces it with this: anyone can spend or anyone can pay modifier to that flag value. So you can end up with a transaction where anyone can pay into it and anyone can spend it, because you haven't signed any of the inputs and any of the outputs. So I could, after the fact, add another 1 Bitcoin into that transaction, and it's not going to invalidate the signature that originally sort of created the transaction. And that's really useful for creating, say, a crowdfunding mechanism. So you lock the outputs. Oh, this is going to go to that family whose house just burnt down, but we can add successive inputs after that's been generated, so everyone knows, oh, it's definitely going to them. They've only got $100 so far. I'll put in another $100, and it builds up that transaction over time. Or similarly, we can use the sig hash flag value to sort of create flexibility in the outputs. I'm going to give my kids $200 for uni fees or something, but they can spend it on textbooks and whatnot. So it's kind of like giving them a check. You know, you've given them that much money to spend, and then they can still add those outputs into it. And really there's, you know, sort of a whole range of flexibility that can occur in that space. And the hash of the sequence is really committing the sequence value is a value that's applied to each input, and it will specify whether it's the final time that we're going to spend that input, or if it's not the final time that we're going to spend it. So there's 4 bytes there that can be modified. So you could start with a value of 0 and have to increment that a bunch of times, or you can just sort of leap through, or you could do something, say, where you go, instead of 4 bytes or 8 Fs, you might do 7 Fs and a as the last character. And what that's going to do is say that there's confirm it. Oh, we need a certain round of negotiations. We want to have 6 back and forths that we can pass this transaction to sort of negotiate. And so you go, okay, we're at the 6 less than the maximum value. Now I've passed it to someone else, and they can increment that input value and change some other condition of the transaction, and then they can pass it back. And you go through these, but it says, okay, we've only got 6 rounds, because after 6 it's going to be the final sequence number, and then that transaction can be mined into a block immediately. So a transaction can't be mined into a block while an input has a non-final sequence number if its end lock time value, which is that overall transaction lock, has passed. So if that end lock time specifies a block height that's in the past, or a Unix timestamp that's in the past, and you have a non-final transaction flag, it can be mined. But if you have end lock times are a value in the future, and you have a non-final transaction state or non-final end sequence, then you won't be able to process that transaction. So that's allowing you then to create these things we've called payment channels, and that will be sort of delivering content through Bitcoin transactions. You might say, I give you a packet of a larger file. I'll give you a little chunk. Then you add another 100 Satoshis to the transaction. Then we increment that sequence number, push it forward again. And all that is occurring off-chain, and it doesn't need to go on the chain until you want to resolve that final transaction state. So you've passed then a HD movie to one another through those Bitcoin transactions, which have the security of having that updated end sequence number, and more value has been committed to that transaction. And at any point, if it ever, the channel drops out, you've got that latest state to push to the network, and maybe you might end up getting ripped off for a couple of frames of the movie. So it's gives a lot more granularity down into that content delivery without having the involve sort of like an escrow or something like that to intermediate between, getting the full object and having paid in full for it. We've got a course that's coming out, which is Introduction to Bitcoin Script, and that was written by Brendan over here. And it's going to be great when it comes out because it really is, explaining everything that we've got in here. So we've got, an introduction to Bitcoin and script as an analog of Forth and some of the history of Forth, a transaction breakdown, and then, some of the rules around scripting. And then we've got an introduction to all the opcodes, and they're broken down into their various segments with some examples and stuff. Then we go into our, the examples of the different simple scripts. So you can say public key hash transaction here. So op dupe, op hash 160, public key hash, op equal, op check sig. And the things that you push onto the stack are the signature and the public key. So we imagine these two bits are going to precede this. So we have the signature going onto the stack, then we have the public key going onto the stack, then we duplicate it with op dupe, so we end up with two versions of the public key. Then we put that second version of the public key, which will be on the top of the stack, through the hash 160 hash function. And then we will see if it is equal to the public key that was provided. And then we will check the signature on the message against that, using that public key, and it will verify whether or not, yes, that is a valid signature for the public key that we have on our record that script has been locked with. And then when we were looking at what Shaway was doing with incrementing the, creating that ability for loops, the genius thing of what Shaway's done there is he's abstracted away in that that simple loop this entire chunk of code here. So this is the classic op push TX. So each time you're running that loop, this is what's happening behind the scenes. It's just adding another one of those onto the script that's going to go to chain to evaluate that. So the script, the size of the transaction grows much greater than you'd imagine for simply incrementing a loop. But what this whole section here is doing is, rather than the node evaluating that, that it can create that same pre-image that was then hashed and signed, it's allowing that pre-image to be pushed onto the stack itself as a, you're recreating it by slicing off little values from the raw transaction data, adding in some values that you're looking up through your own service to see the value of the UTXOs that are being committed. And then you're doing these little operations of, slicing off, splitting off a few bytes, concatenating them to a value, and you're building the raw data of that transaction pre-image on the stack. And it can allow you then to say, oh, I need to check things against that. Remember how we checked against the script context? So you're checking on the stack with those simple calls that Shaway's written, sort of identifying little specific parts within this. And each time you're incrementing that I, you're adding a whole other block of this onto the script that's going to be published onto the chain. So that's, it's a huge saving that has been done there to make people not have to write that. But there are times when it is still advantageous to write in Bitcoin script. And, Brendan was showing me yesterday the output from an sCrypt transaction, and it had the script in it, but it sort of did these operations of take one step forward, take one step back, take one step forward, take one step back, and it didn't really, it was a few opcodes that were left there, but essentially the same thing could have been achieved with just one value and verified against another value. So they're like an artifact then in the script that's generated by compiling, Shaway's TypeScript down into Bitcoin script. There's, I don't know how you've done it to begin with, but there's still processes in there where, there might be some leftover values that kind of cancel each other out, but didn't need to be in the script to achieve the same functionality. And so maybe over time there will be a refining or a refactoring of these functions and stuff that Shaway uses under the hood to produce that functionality in script TS. So hopefully that can kind of bridge the gap into what Brendan's doing. So Brendan's going to show you a heads and tails game in script, and you know how that can be done. And he writes his stuff in Excel and simply just builds the script, you know, using Excel as his stack visualizer. And he'll show you all there. But I thought if he just jumps straight in there, you might be a little bit confused as to what's going on, like, because it takes a little while to wrap your head around it. But you know, yeah, this is allowing us to create these Turing machines, and it's allowing us to, you know, so that's, you know, where's the pre-image? Essentially, we're using that to check values from the pre-image, and that would be that script context that Shaway is using. Yeah, this isn't public yet. So we're working on, Brendan's got to review the animations that are being produced. So, because it's also abstract. So we're creating, you know, stack visualization GIFs, and it will show the different opcodes being sliced off. And if we're using as well the alt stack. So are you guys familiar that there is 2 stacks in Bitcoin? So it kind of, sorry?
Yeah, again, you mentioned it.
Mentioned it casually. Yeah, but that allows you to, you know, instead of having to recreate it always on the stack and then move through and then sort of recreate it again. If you're doing it that way, the single stack will just, you know, get huge, but otherwise you can sort of push values onto the alt stack and bring them on to the main stack to perform operations upon, then move it back over there, and it allows you to sort of slice through more of the script codes that are sitting on the stack, grab it again, bring it back in. So that's the mechanism by which it, you know, you sort of can create these efficient unrolling these loops. But yeah, I'm looking forward to it being out, and I'll be sure to pass it, let Jack know, and you know, I'll be sharing this content, you know, with him so that you know, future cohorts of you guys can be exposed to it. Have we got any information here on the SIG hash? I think you can find it on the wiki, the SIG hash, but it's definitely worth experimenting around in. If you want, I've got a little video that I've made a tool that you can sort of build a BSV transaction from scratch on the reg test. So it just takes like a few minutes. Will there be sound? I'll probably just be able to narrate what's going on at the same time. Yeah, that's probably good. Yeah. So here, this is connected to a reg test node. So a reg test node is just an isolated Bitcoin node with a few of the parameters changed so that you can mine blocks instantly. You don't have to go through the proof of work process. So when you press the generate key pair, you're just making a request to that node to provide you with a private key and a public key pair, and then the subsequent address for that. You know, and those addresses, they're M, so you can know that they're for the reg test or the test network, and then we can mine some blocks against the key that we're going to select from that index. And when we mine those blocks, you get a bunch of these data fields. So these are not everything that you need is included in this to recreate the pre-image. But when we can start with creating a transaction. I think I'm going to end up refactoring this because I started building the transaction here to start with, but it's kind of a redundant step because you don't really need to go through and specify all these values at this point because we're going to be creating the pre-image. So you're better off just creating a transaction by generating the pre-image for each input that you're going to spend from scratch rather than building this bit out. But I want to have this as a resource that's available on our website. So when students are doing our introduction to Bitcoin script, they can experiment in here with crafting their own custom lock scripts, because there's no real reason why you need to have you know, a digital signature and stuff on the transactions just for the node to evaluate it. You use the signatures so that you can pass these messages across a public channel without having to worry that people are going to intercept it and slice their paying data into that transaction. So the digital signature allows you to send sort of tamper-proof messages across a public channel. But yeah, when you get provided these responses by the what's on chain or whoever's going to sort of the explorer, or you request these things from the node, some of the values come back as decimal and some of them come back as hexadecimal. So I've just done a conversion there where I converted the decimal representation of a Bitcoin to the decimal representation of the Satoshis, then the Satoshis to the hexadecimal, and then switched the endianness around, which is the way that they're sort of, whether or not they're fed with the biggest number into the machine, or whether they're fed with their smallest one first. So this is where I'm creating the pre-image. So when we expand that pre-image container, it will, it's tricky not knowing how slow I'm going here. We've got some of the sig hash help that just specifies. So this is, if you've got that different sig hash all, then these are the value fields of that pre-image, which are going to be replaced with zeros. And that allows you to add in these other inputs or outputs after the transaction has been signed. So I'm just probably explaining this. Let me just jump through into the... So now, yeah, you're just going through and you're sort of putting the sequence numbers in there. So that's all the Fs. You're then the script code, so it's knows how long this script is going to be. Then it adds the script length itself, or the script itself. Then I had to, when I put the value in of a transaction, I had to account for the fact that some of those Satoshis are going to be collected as fees. So you have the value of an input that you're spending, but when you want to spend that as an output, that output value has to be less than the aggregate of all the inputs for the node to collect whatever is the fee policy of the time. So yeah, we're going through, and then we're locking as well the value of that previous transaction that funded it in here. So I thought it might be a bit better if it was being narrated by me, but essentially, let's jump through to so that there is the pre-image. So this is the version 010000. Then we would have the hash of the previous outs, which is from that 632 across to I don't know, wherever it is. Then you'd have the hash of the sequence number. You can see here those Fs are the sequence number itself, the zeros somewhere, probably the end lock time. This 41000 there, that's the sig hash flag. So that sig hash flag, then when they will also then append that to the signature. So if we just move a little bit through, So now I've hashed that pre-image and created the sig hash there. And then in that next table down, you can see I'd enter the private key against that unsigned sig hash. And I would specify, again, the sig hash flag. So that sig hash flag is appended to the, I've grabbed the key there, 41, and then it's now provided the signature. And you can see the last bytes of that signature is the 41 again. So the node gets it and says, okay, now I know when I'm creating my pre-image, I know which values of it are going to be zeroed out with the bytes, and I can then verify the signature, because otherwise it doesn't know of the sort of 6 different possibilities which one it's going to be. And if you have lots of inputs, it would just be a complete guessing game. So you need to specify in the pre-image itself, so locking the sig hash flag behind that signature, and as well specifying it after the fact. But this is only necessary on a script that has that check sig opcode in it to be evaluated. There's no reason why you couldn't make a script that was op3 op equals, and all that's going to be needed to be provided to spend that transaction is a 3. So your unlock script would be provide 3. So the 3 gets pushed onto the stack. It has the 3 already on the stack from op3 op equals, and it says, does 3 equal 3? Yes, that would be a valid transaction. But you put that to a public channel, and it's not a signed transaction, and someone else can extract it from you. But just trying to reduce it down to the simplest explanation as that, it's just, does a left-hand side equal the right-hand side in that equation on the stack? And you can do all kinds of functions on either side to make sure that, you're able to get a true response for that Boolean. And then, there'll be the signature itself is provided there, the public key, and then that will generate that unlocking script, which is then, the size in bytes and the signature and the pub key, which we saw for, that's in specific for a P2PKH transaction, pay to public key hash. But there are different ones that, would need to have a different validation logic. So in the event we did a multi-signature transaction or, a pay to R hash, or there's different types of transactions, and they're all going to have their own way of checking the signatures. Some inputs can have multiple signatures. So it gets really complicated, and that's what you need Shaway's tools. But hopefully Brendan can show us something really cool that can be done in native script, and might make us better equipped to evaluate both sides' positions in the debates, discussions that are going to go forward. So, cool. Yeah.